Dr. Reddy has completed his PhD from Dr. H.S. Gore Central University and postdoctoral studies from Sangyong University, South Korea. Sir has more than 12 years of experiences on battery material and their application in EVs. Dr. Reddy currently working as an associate professor, Department of Physics, PVRIT, Hyderabad College of Engineering for Women, a premium engineering college in Hyderabad. Previously, Dr. Reddy worked in VIT University and KL University as an assistant professor. Sir has also published more than 50 papers in reputed journals has been serving as a reviewer for many reputed journals. Sir has given many invited talks and keynotes lecture in the various countries in reputed international conferences. And Sir has also received many awards and honors for his contribution in research on energy storage devices and also in academics. Dr. Reddy having 3 patents for his credit. Dr. Reddy also having a H index of 23 and having more than 1700 citations. Dr. Reddy is also a life member of Electrochemical Society of India and visited about 12 countries. And now I would like to hand over the session to Dr. Reddy for the presentations by the participants. Over to you, sir. Sir, your mic is off. You are not audible.
Sure. Yeah, thank you, Pushpendra.
Yes, sir.
Yeah, is it okay now?
Yes, sir, it's okay.
Okay. Yeah, good morning, all. Yeah, in this session, we are having total 7 presentations. Okay. Please try to conclude within time, and we need to allot time for questions also. The first presentation today in this session, yeah, by Chavi Mitrawal. Yeah, the presentation entitled Manganese Oxide Modified Microstructure and Electrical Analysis of High Temperature Applications. Okay, actually Chavi Mitrawal, she is from Banasthali Vidyapith.
Yes, sir.
Yeah, you can share.
Good morning.
Yeah, good morning.
Okay. Good morning, everyone.
Good morning. You can share and you can start, Chavi.
Yes. You can see my screen, sir?
Yeah, yes. You can do full screen.
Okay. Good morning, everyone. I am Chavi Mitharwal. I will be presenting on the topic MnO2 modified CSBT, macrostructural and electrical analysis at for high temperature applications. I am working under the supervision of Dr. Supritam Mitra in Vanasthali Vidyapith. So nowadays, there is a need of sensors and actuators that can function at elevated temperatures in industries, for structural health monitoring in industries such as chemical, energy, automotive, oil and gas, especially in high temperature industries. So out of all the options available, we will be focusing on BLSFs such as CBT or CHBT due to their high TC, low dielectric loss, low electrical conductivity, but it also has a disadvantage of low dielectric coefficient. So in order to improve the electrical properties, we will be in order to improve the electrical properties and also to improve the piezoelectric coefficient, here we have substituted Ca2 plus by Sr2 plus in the composition CSBT. And in order to furtherly improve the properties, there is also the doping has been also done with MnO2 with different concentrations. So we have prepared the different compositions of CSBT with different concentrations of MnO2, but simple conventional solid state reaction which have been further converted to pellets. The sintering of pellets has been done at different temperatures ranging from 1050 to 1080 degrees Celsius. We have used XRD to check the purity of the phases. SEM and EDS has been done for macrostructural and elemental analysis, and further electrical properties have been analyzed by impedance analyzer. The results and discussion are as follows. First, you will be seeing the XRD graph. The highest peak has been observed at 119, which matches with that is expected of the exclusive feature of BLSFs. Here we can see that the unit cell volume with the concentration of 0.08 is higher, and we can Raman spectroscopy has been done in order to observe the phonon modes at different wavelength. And here you can see the EDS spectrum elemental mapping of especially for CSBT4MN. And here we can see that MN has uniformly distributed in over the all composition. Now further to the SAM analysis, here we can see the SAM macrographs of polished and thermally etched samples of CSBT-MN. Here in the E graph, E diagram, E figure, you can see this is basically of the fractured surface. Here you can see we have observed plate-like features, basically which is basically due to the growth in higher growth in the C axis compared to the A or B axis, which is a nice feature of BLSF. Here we graph we can see relative density and aspect ratio of MN content. Here you can see the value of W upon L, that is thickness upon length, changes notably with the addition of MnO2. This is due to MnO2 does not accelerate grain growth, and pores are reduced with the addition with the increase in the concentration of Mn. And here towards the right side, you can see relative permittivity versus temperature graph of different concentration at frequency 1 kilohertz. There is a this peaks verify that there is a transition from ferroelectric phase to paraelectric phase, and this also tells us about the Curie temperature. Here in the inside graph, you can see that TC first decreases, then increases, and furtherly in the B diagram, you can see dissipation factor, and with the temperature dissipation factor usually is constant up to 400 degrees Celsius. Which tells that we can get good piezoelectric properties. And in the C diagram, this is basically for the 0.04 concentration, and below you can see dissipation factor, which proves that dissipation factor is low, loss is low. So this is a good composition. Further, AC conductivity variation with frequency at various temperature has been seen. The AC frequency, the AC conductivity remains constant. First remains constant, then increases. And towards the left side, you can see the variation of the DC conductivity. The AC conductivity has been derived to the Johnson's law, and DC conductivity is with the help of the different formula, has been derived with the help of different formula. And complex impedance plot of CSBT4MN at different temperature is you can see here. And complex impedance equivalent permittivity with equivalent parallel RC circuit capacitance and resistance with temperature for CSBT4MN concentration can be seen. The capacitance is higher at the 600 degrees Celsius because there is a transition from ferroelectric to paraelectric phase. And you can see the semicircle graph in Z double dash versus Z dash plot, which verifies that this is a single relaxation process, and impedance is mainly due to the grains. So we can conclude that modification of MnO2 does not significantly change the crystal structure. However, an improvement in density has been observed. Little variation of Curie temperature is seen with the increase of the Mn content. For a small concentration of Mn, ceramic shows an insulating behavior. Out of all the doping, with the doping of Mn 0.04, it shows high TC relative permittivity of here, dissipation factor which is less than 0.05%, and DC conductivity, better DC conductivity has been seen. So we can conclude that with the CSBT with concentration of 0.04 Mn is a favorable candidate for high temperature electromechanical applications. Thank you. Any questions?
Yeah, thank you, Chavi. Any questions now? We have time for 2 questions. Any questions from audience? So I have one question.
Yes, sir.
Actually, in your XRD, I have observed. Have you done any ritual refinement for your XRD?
No, 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 sir. No discrimination.
Okay, not.
No, I have not done that.
Whatever sample you prepared, for which application point of view you prepared?
Sir, for high temperature electromechanical application for sensors and actuators that can work in high temperature industries
Okay, okay.
for structure health monitoring.
And what? How much conductive you got? AC conductive, how much you got? DC I observed 10 to the power -6.
Yes, sir.
What about AC conductive? How much you got? AC?
Sir, AC conductivity, you can see the graphs, sir, at different temperatures for CSBT 4 mn.
That room temperature, how much?
Sir, room temperature, I have to show the value, sir.
Okay. Any more questions from audience? If there is no questions, we will move for next presentation. Okay, Chavi, thank you very much for your nice
Okay, sir.
presentation. Now we will move to second presentation. The second presentation from Anshika Bagla. She is from Banasthali Vidyapit. She is going to present on dopamine modified PVDF based nanocomposite for storage and flexible energy harvesting applications. Yeah, Anshika, she is from Banasthali Vidyapit. You can start. You can share your screen.
Yes, sir. Good morning, everyone. So is the screen visible, sir? Is the screen visible, sir?
Yeah, screen is visible. Yeah, right. Oh, it's okay. It's okay.
So, hello everyone, I am Anshika Bagla. I am a research scholar at Department of Physical Sciences in Banasthali Vidyapit. I am working under the supervision of Dr. Supratam Mitra, who is Assistant Professor at Department of Physical Sciences, Banasthali. So, I'll present my paper of dopamine modified BCT, BZT, PVDF based nanocomposites for storage and flexible energy harvesting applications. So the outline of my talk will be, first I'll be discussing about the motivations, then I'll go to introduction part, and then some experimental details and the methodology used. Finally, I'll discussing about my results and discussion. So the motivation starts with a well-known topic, that is energy crisis. Owing to the escalating worldwide concern over energy calamity and environmental issues, there's a need to look for an alternative renewable source of energy. Energy harvesting basically is scavenging energy by conversion of abundant energy present in our environment into electrical energy or electricity for use in powering low power devices like Internet of Things, that is wearable health monitors, smart factory equipments, wireless inventory trackers, and many more. Basically to power the devices which are of low power and need to be charged repeatedly. So ambient energy to put into use. Why? Because mechanical energy is the most abundant energy source and is easily convertible into other usable forms. Piezoelectric nanogenerator to use to the rescue. Piezoelectric nanogenerator is a type of technology that convert mechanical energy to electricity. Piezoelectric nanogenerators are the approaching alternative choices for scavenging different types of wasted mechanical energy. And now, why to use lead-free piezoelectric material? There is increasing research into utilizing lead-free piezoelectric ceramic materials for energy harvesting because of the toxic environmental effect of using lead-based piezoelectric ceramic material. And also, European Union has restricted the use of lead-based materials. Now my introduction start with piezoelectric nanogenerators. What piezoelectric nanogenerator is? Piezoelectric nanogenerator is a promising technology for harvesting mechanical energy because of its ability to convert mechanical energy to electrical energy by means of piezoelectric material. when an external mechanical force is applied, these material accumulate electric charges. Piezoelectric or ceramic material have been used for the assembly of these charges. As we can see, there is building and bridge oscillation, human motion, vehicle vibration, as in picture it is shown. These all are low energy source. The vibrations, which are low energy source, which are converted into several applications by the use of piezoelectric nanogenerators. Several applications like powering shoes, pacemakers, tire condition monitoring, and also there are many application areas like sensors, actuators, filters, batteries, frequency controlling devices, wearable and implantable devices such as pacemakers, heart rate monitors, implantable drug pumps, brain pacemakers, and etc. Now, polymer composite is used for energy harvesting application. Now, what polymer nanocomposite is? Polymer nanocomposite is a composite in which we combine a polymer matrix with some kind of nanomaterial. In making of polymer nanocomposite, the aim is to take exceptional property like strength, stiffness, electrical and thermal conductivity on a standard material. More specifically, we want to take a very small amount of nanomaterial and use it to significantly enhance the property of bulk material without a significant increase in its weight. Some piezoelectric polymers are PVDF and PVDF TRFE. PVDF is one of the most attractive and highly investigative candidates for mechanical energy harvesting applications among polymer materials. The feature of PVDF, such as high piezoelectric coefficient, excellent stability, and desirable flexibility, promoted its application in different nanogenerator. On the other hand, PVDF TRFE also are polymeric material typically used for electronic application. I chose PVDF for my work because of cost effectiveness. PVDF TRFE is more expensive than PVDF. Now, as I have shown in the diagram, there are three phases of PVDF: alpha phase, beta phase, and gamma phase. These are the phase diagram. Due to the anti-packaging of molecules, beta phase is highly electroactive. Alpha phase and gamma phase are electroactive, but not that much as beta phase. Beta phase is highly electroactive. So, for using in electronic devices or energy harvesting devices, my aim was to achieve high beta phase, and there are so many ways to enhance beta phase. One of them is adding nanofiller, because nanofiller enhances beta phase and sometimes modified nanofillers. So the nanofiller I used was BCT VZT. Now, why I chose BCT VZT? The answer is because BCT VZT is an environmental friendly piezoelectric ceramic, which is obviously environmental free, which is obviously lead free. That is a promising alternative to lead-based piezoelectric material that can replace PZT, whose toxicity is well known. So the experimental details starts with preparation of BCT VZT by Sol gel method. The BCT VZT was then divided into two parts. One is WODA, that is without dopamine added, and the second one is WDA, which is referred as WDA, that is with dopamine added. So there were two samples after that. One is dopamine added and what is without dopamine added. Then the PVDF was mixed with DMSO and heated at temperature of 80 degrees Celsius. When the pellet of PVDF was completely melted, BCT VZT nanofiller was added slowly with different weight percent from 10 to 60. Then it was stirred continuously for 12 hours, then sonicated for 90 minutes for mixing. Then a homogeneous slurry was prepared, which was cast to a clean petration capped at 60 degrees Celsius for solvent evaporation. A composite film of around 50 micrometer thickness was generated. Then the film prepared was sputter coated on both sides, leaving 1 mm from the edges. Then the sample was tested continuously, increasing DC field, and the leakage current through the sample was monitored to check breakdown strength. The test of energy harvesting performance was done by based on human motion. I used beating of fist for recording the mechanical energy. The composite film was cut into a rectangular shape having an active area of 4.5 into 1.5 centimeter square and pulled under 15 kilovolt per mm DC electric field for 6 hours at room temperature. For mechanical excitation, a periodic beating with a fist was used. The open circuit voltage and short circuit current density was measured by a digital oscilloscope. And to calculate maximum power density, a load resistance RL varied from 1 kilo ohm to 10 to the power 6 kilo ohm was attached in parallel to output. Now these are the results, the XRD results of these are two graphs. One is without dopamine added, one is with dopamine added. As we can see, the alpha and beta peaks by adding dopamine, beta phase was enhanced. There are two beta peaks, sharp beta peaks, and in without dopamine added, there is one beta peak. So beta phase was enhanced by using dopamine, and these are the same images. The upper one ABC are of with dopamine added one, and DCF lower one are without dopamine added. It was seen that lower filler content gave larger grain size, and higher filler content gave smaller grain size. Here I am talking about filler content means I changed filler from 10% to 60%. So for each like 10, 20, 30, 40, 50, for each filler the results was recorded. So here here you can see filler particles, then dopamine is added, then this is dopamine modified filler, then this modified filler was added with polymer, and this is the structural diagram of the final filler which was casted further. Now these are dielectric permittivity, dielectric loss tangent, and AC conductivity results. In each results, it was it was seen that dopamine added filler gave better result and gave a better beta phase. Then these are breakdown strength, and also and here the cold one, so the film which was cold under 15 kV per mm results is given, and also uncold which was not cold in high voltage. These are the difference of cold and uncold films, load resistance versus V output, and the cold one gave better results than comparison of uncold films. It also enhanced its beta phase by applying high voltage. Now this is the final DSO result of cold and uncold film. The charging was for uncold film. V output was seen 0.73 volt for charging at time 18.04 second, and the discharging time it took was 30.05 second. For the device which was cold under 15 kV per mm high voltage, the charging was seen to be 1.47 volt, which is obviously higher than the uncold one, and in time 16.21 second, and the discharging time was 29.49 second. Thank you.
Thank you, Anshika.
Thank you, sir. Any questions?
Any questions from audience? Yeah, I have a few general questions, Anshika.
Yes, sir.
What about with the cost wise?
What, sir? I can't hear you.
Cost wise.
Caste wise
Means it's expensive or cheaper than existing one?
Achha, cost wise, okay.
Yeah.
No, sir, it was not that much expensive because I have used the PVDF, which was obviously cheaper than PVDF TRFP, and the device was prepared by using the filler and PVDF and everything, which was obviously cost effective, so that we can use it in low power devices for charging, and it will be not expensive.
One more thing, actually, piezoelectric materials generally those are brittle in nature.
But
But
sir,
here-
I can't hear you.
Yeah, actually, these piezoelectric materials are brittle in nature generally.
Yes, sir.
Yeah, here you are added PVDF that will increase the mechanical strength of your material, I think.
Yes, sir.
Yeah, generally for converting that mechanical energy to electric energy, we need to apply more stress.
Yes, sir.
Will it be bearable that stress, that material?
Yes, sir, it is flexible. The device is flexible in nature. You can twist it. It can bear stress. And also the device was meant that meant in way that when you apply mechanical strength, you can apply it and the strength as much you want. It is flexible in nature.
Okay, okay. Thank you, Anshika.
Thank you, sir.
Any other questions from audience? If there is no questions, we will move to next presentation. Next presentation from Jitendra Kumar. He is
Thank you.
from, yeah,
Thank
thank you, Anshika.
Thank you, sir.
Next presentation from Jitendra Kumar. He is from Jay Narayan Vyas University, Jodhpur. Yeah, he is going to present on study of structural and electronic properties of HGTE using ab initio method. Yeah, Jitendra, you can share your screen.
Good morning, sir.
Yeah, good
On
morning.
behalf of International Conference on Advanced Material in Innovative Technology, presented by Amity University, Rajasthan, Jaipur, myself, Jitendra Kumar, research scholar, Jay Narayan Vyas University, Jodhpur, under the supervision of Dr. Uttam Paliwal, sir. The title of my paper is The Study of Structural and the Electronic Property of Mercury Telluride using ab initio methods.
Yeah, Jitendra, you can make your full screen.
Yes, sir.
Yeah, you can make full screen.
Myself, Jitendra Kumar, research scholar,
Full screen.
Jain.
Sorry, full screen. Slide
Yes,
show.
sir.
Actually, your presentation is not in full screen. Just
My
press F5. Press F5 for making full screen. Full
yes, sir.
screen.
Yes.
Yeah. Yeah, right. Good. Okay, Ji. You can continue.
In this present work, the structural and the electronic property of mercury telluride using ab initio methods. In this present work, we calculate the structural and electronic property of topological material like mercury telluride. In this method, we use the ab initio methods. Applying the density functions theory, we determine the structural parameter of mercury telluride like lattice constant, its optimum volume, and its corresponding energy. We use different kind of exchange correlation functions with pseudo potential to see the effect of structural property of mercury telluride. In this work, we use four different type of exchange and correlation functions, that is Purdue-Wonge, Purdue-Wong, Purdue-Zunger, and Hukon. In this all four type of exchange correlation functions, PBE and PW91 are the generalized gradient approximation, where the PZ and Hukon are the local density approximation type functions. In this way, we get four different type of combinations, and we obtain the lattice constant, such as this slide show the variation of total energy versus E cutoff. In this, using the graph, we can show that after the E cutoff 100, the total energy will never suddenly decrease. We can say it is almost constant in this duration. That's why we can say the total energy occur, that is our 100-degree Rydberg. After that, I vary the total energy versus K grades points. After in this section, you see that the K mass point for mercury telluride is 8. We can use higher value of K and K for the better simulation like 10, 12, etc., etc. This is my work in which the energy and the lattice constant calculation by the non-conserving pseudo potential, we obtain the lowest energy from this region up to 495 volume. We can get that the optimum volume, and that corresponding the total energy, that is minus 13.430 Rydberg. In this way, the present slide also show the variation of mercury telluride with lattice constant and total energy cutoff. We can say further there is a whole this type of the result obtained by using various kind of exchange and correlation functions. That may be sometimes LDA with GGA. These results are suggest the final result and the conclusion is that after you say that the result 6.45 and 6.53, these result are the LDA type result. In LDA type result, we can say local density approximation, and local density approximation, that is the totally based on non-interacting, we can say uniform electron distribution. Uniform electron distribution, that the results show the better ground state energy with respect to other these. Other these are the GGA type functions. In GGA type functions, we can use generalized coordinate. Yeah, we can say the gradient of density functions theory, and this result is slightly overestimated to our predicted result. And the overall, we can say the lattice constant of mercury telluride is approximately 6.47, and these results show 6.45, which is very near to the experimental value of mercury telluride. And after that we get this is the final result. We can say the E cutoff is 100 Rydberg constant corresponding K point grid value 888. It observed that the LDA functions Purdue Wang Wukong give the value of lattice constant closer to the experimental data, while ZGA functions Purdue Bunge spin orbit generalized gradient Purdue Wang are overestimated. It in an SCF calculation, we obtain the highest occupied and lowest unoccupied level are equal, that is equals to 9.3470 electron volt. It suggests that the mercury telluride is a topological material. That is from my side. Thank you, sir.
Thank you, Jitendra.
Yes, sir.
Any questions from audience? It's completely related to theoretical work. It's good work. Yeah, thank you, Jitendra, once again.
Thank you, sir. Welcome.
Yeah. If there is no questions, we will move to next presentation. Okay, Jitendra, you can stop your screen sharing. Right. Yeah, next presentation by Seema Verma.
Yes, sir, I'm present.
Yeah,
Good morning.
she is also from Banasthali Vidyapith. She is going to present on photovoltaic devices based on metal oxide nanocomposite with polymer in active layer. Yes, Seema, you can start.
Okay, sir.
Jitendra, you can stop sharing. Yeah, right.
Sir, is this visible, my slides?
Yeah, right. You can do full screen.
Yeah. Sorry.
It's good. Okay.
Good morning, everyone. I'm Seema Verma, a research scholar under the supervision of CMS Negi and Saral Kumar Gupta, sir, in Banasthali Vidyapith. Today, I present my work. This topic is a photovoltaic devices based metal oxide nanocomposite with polymer in an active layer. These are the content of my presentation: introduction, device structure, result discussion, and conclusion. So now, in this work, I used in a PTA. It means in my topic, I used that the polymer, which is an organic material. So this and polytriaminine PTAA is a P-type semiconductor with the highest mobility up to the 10 to the power minus 2 centimeters square per volt second. This is the PTA is a stable glassy polymer and has a good ionization potential for thin film diodes. And PTA and metal oxide, zinc oxide nanoparticles are used as an active layer of the devices. Here I use this organic material within a metal oxide. I use this. I'll synthesize in a nanocomposite form. And sorry, sir. Okay. Sir, can I continue?
Yeah, you can.
Okay. Here we use that the PTA and the metal oxide ZNO nanoparticle as an active layer, and here I compare the two devices, which is first is it's only a PTA based devices and another is a PTA ZNO nanocomposite devices. Okay, so now there is a device structure of my device, which is an ITO P.SS PTA ZNO nanocomposite TiO2 and aluminum, and another one is the only PTA based devices. So here we use an PTA can be coated as a substrate material, which is used for the transportation of holes in the fabrication of many devices like perovskite, solar cell, polymer, light emitting diodes, and organic field effect transistor. Okay. And then now here I compare the photovoltaic, optical, and electrical performance of the both devices, which is the nanocomposite and only the PTA based devices. Okay, these are the schematic diagram of my schematic structure of my device, where here you see in this figure A with a glass substrate over the glass substrate ITO, which is then a conducting material as an anode, and where over the P dot PSS, PTA, ZNO, and TiO2. These all materials will be deposited or layer by layer through the solution process, like a spin coating technique, and then finally another electrode, which is the aluminum as a cathode, will be deposited through the thermal vaporization unit. Okay, now we know all the mechanism of this devices, which is depend on the four mechanism. The first one is a light absorption, second is a charge generation, third is a charge separation, and the fourth is a charge collection. Now here you can see this is the corresponding energy level diagram. And this is when light is illuminating on this active layer. The active layer. Firstly this active layer, basically the light is come through the glass substrate, and when we discuss about this the energy level diagram, the light is falling this active layer part. So the photon light is absorbed. This layer, this active layer portion will be absorbed. The number of photons will be coming through the sunlight or the sources, and then this LUMO of this organic material, which is the PTA, is an organic material. So it will create the charge generation, which is an exciton, electron, and the hole pair. Okay, now the third step, but the third generation is the charge separation. The charge separation, it means this ETL or HTL, it means the electron transport layer or hole transport layer will be transport the charge carriers smoothly throughout their anode or cathode. Okay, now this is the energy level diagram seen, and then finally we'll collected the holes in this aluminum, and now collected to the electrons to the ITO. Okay, now these are my result discussion which will perform, which I characterized, which I characterized. Observe the optical properties. So these optical properties will be performed through a UV spectrometer with full wavelength from 300 to 800 nanometer. Now you can see the figure. The pristine PTA have absorption peak at between 350 to 450. 350 to 450 nanometer, and then metal oxide ZNO have absorption peak at the 370. So now you can see at the red one, you will see that the metal oxide will be absorbed all the organic pristine PTA absorption peak. So here we seen the better dispersion of nanocomposite of PTA and the ZNO. Okay. And these are the surface morphology and the Raman spectra. You will see that the better dispersion of the ZNO nanoparticles and PTA. So here, so this better uniformly dispersion resultant shows the enhance the device performance. A better dispersion gives the idea about the less pinhole, less defect, less threads at the thin fields. So this will be give the ideas to be. We will go to the further characterization. This is the same image of a 1 micrometer range, and this is the Raman spectrum of the composite nanocomposite thin film. So here we seen that the compositional information of the PTA and ZNO properly. So here properly is seen that the particular ZNO and the PTA absorption, PTA Raman shift peak. Okay. Now this is my electrical characterization. So here we see these are the I'll already naming the device of D1 and D2, which is the D1 is the PTA ZNO based, and D2 is the only PTA based devices. Okay, so so here you see I'm from figure A. When this is the electrical characterization will be examined by the solar simulator technique at room temperature. Okay, now when it is in a dark, in a dark condition, you can see, and the device one, D1. So it is seen from the PTA ZNO nanocomposite film. This is coming from to the -70 micrometer, and from this and you can simultaneously see in the figure B, you can see at the dark, it will be coming is nearly to the zero. But when the light is illuminating at the particular power intensity, so it will be seen that the device D1 will be seen that the great current, which is approximately at 200 microampere. Comparingly to the if you're comparing to the device D2, it was a very less, which is a 40 microampere. Okay, now so we've seen that the PTA ZNO based devices or based photodiode or photovoltaic devices will exhibit a great current. Okay, now these the figures. See, we've seen this both graph, this both line. We've seen there's the red one, D1 dark and D2. So we've seen this is the exhibited a great current in a device D1. But we will use the device as an application purpose like photodiodes, photovoltaics, or polymers, organic light emitting diode. So can use another light. So we use the device in an illumination condition. Okay, so these are my electrical characterization, and now the conclusion. The nanocomposite device comprises the composite of ZNO and PTA having fabricated and characterized. Interaction between ZNO and PTA has been confirmed by the study of Raman and UV absorption spectra. As a result, the composite-based device is a relatively large current level under dark condition and illumination condition. The best optoelectronics performance was exhibited by the blend or composite of PTA ZNO-based devices due to the suppressed recombination and better interface quality as revealed by the dark current. This was illustrated the great potential of PTA ZNO nanocomposite for application in a wide range of optoelectronic devices. Okay, thank you so much, sir.
Yeah, thank you, Sima.
Okay.
Yeah, any questions from audience? Any questions? Yeah, Sima, I have one question. Is it the solar cell device also, no?
So yeah, I'm trying to make it a solar cell devices mechanism, but it will be it will not perform the solar cell, but we will use as a photodiode or photodetector.
Have you calculated any efficiency for this device?
No, sir, it's not coming to any efficiency. So as we can say that this is a photodiode or photodetector device.
Okay, okay. When
Yes.
when we want to use a solar cell, that time we need
Yes,
to
I'm
calculate
trying
the
to make a solar cell. Okay, yeah, yes, sir.
Yeah, because after observing the structure, that's exactly looks like solar cell structure.
Yes, sir. Yes, yes.
Thank you, Sima.
Okay, sir. Thank you so much, sir.
Any questions from audience again? Right. Next presentation from Shiv Kumar. He is from Periyar Maniamma Institute of Science and Technology, Tanjavur. He is going to present on ab initio design of nanomechanical structures, a review part. So Shiv Kumar, you can share your screen.
Yes, sir. Thank you, sir.
Yeah.
Sir, my screen is visible now, sir. Hello, sir.
Yeah, it's good, Shiv Kumar. It's good. You can continue.
Yes. Thank you, sir. Very good afternoon. My topic is ab initio design of nanomechanical structures. I'm Shiv Kumar N. From working as an assistant professor in Department of Mechanical Engineering, Periyar Maniamma University, and I'm doing studying also in NIT Trichy under the guidance of Dr. Ramesh T. In Department of Mechanical Engineering. So my topic is regarding the design of nanomechanical structures. Okay, so these are the earlier described photos regarding nano machines and all in the 90s and 2000. These kind of pictures are floating in the internet and inspire us to getting into the nanotechnology. So So yeah, actually nanotechnology has a huge potential in addressing biomedical equipments and other issues like diseases and other things. The entire things could be solved by designing those advanced nano machines. That is why that is where the industry is presently moving on now. So these now you can see the nano machines that is designed by Dr. Eric Drexler in olden days. And these are on the left hand side at the bottom. I also designed using his tool called the Nano Engineer, so that has some kind of gear kind of structures. And now I'm here on my work precisely focus on reviewing what are the software recent progresses available in producing the molecular gases. Okay, so that is our narrow area I am focusing on now. So actually, when we speak about molecular design, it is broadly categorized into molecular visualization, molecular simulation, and then after post processing works are there. So there are tools which can visualize what all the molecular gases or molecular models we design. Say a simple, very small softwares like JMOL and the big softwares like Nano Engineer one, and the PyMol. These are available available for decades. Okay, so Nano Engineer is very old software from running from 2000. It is available. JMOL is also useful for when we visualize the molecules that we design. Okay, so after designing and molecular simulations is the key part where we have to optimize based on the energy through quantum mechanical methods like basis sets like density function methods, and there are several techniques available. So they are the key fundamental thing is either it align with the molecular mechanics or align with quantum mechanics. So when we speak about molecular quantum mechanics, in nanotechnology, everything is around size of molecules and atoms. Then in that domain, we have to only apply quantum mechanical methods to have a picture of electronic structure of those molecules. Okay, so the softwares available is one is a proprietary, that is we have to pay. That is a Gaussian that already widely known software. And other free softwares backed by the United States government is Games US and Games UK. So these are some widely used packages, similar that can give results that are at par with the Gaussian. So these are we already demonstrate some designs that is done by Dr. Eric Drexler, but the problem with those structures is when we try to create optimize based on quantum mechanical methods, everything will collapse. Okay. So then what is the use of those methods? So that is a big question asked against Drexler, and the problem is when we speak about macro designs like or machineries, then we have straight away design and then go for fabrication. The problem with the molecular world is in between we have a simulation that is interrupting. So when we don't have a optimized geometry based on the quantum mechanical methods, we cannot have that model that we produce, that is called guess, that to be fabricated. Okay, so it is not possible to fabricate those guesses unless otherwise we have a optimized model. So that is the thing. So there are molecular dynamics packages available for huge molecular structures where we cannot use quantum mechanical methods because of lack of computational hardware requirement. These are some MD packages, that is molecular dynamics packages, GROMACS, CHOM, LAMPS, and Tinker. So many molecular dynamics packages involved. They are using Newtonian methods. And these are some ab initio methods based on quantum mechanical roots. Okay, so like ab initio and the Games is one of the widely popular one among these. It is funded by NS of US also. So mostly on GNU or Linux, they have provided packages for quantum mechanical structures. So these are up to this we discussed everything is nearly started earlier before 2 decades or a decade. But now recent there are certain works that is coming to our picture. That is they are try to design based on the DNA. With the help of DNA as a base material, they try to produce some robotic kind of forms that is a kind of mechanical structures. So they have used several tools. One among them is called OxDNA. So this is the OxDNA tool that is used for designing the robotic kind of arm, pick and place arm at the molecular scale by the Chow Min Huang et al. So apart from that, OxDNA, we have a recent tool called CAD Nano that can easily produce nanomechanical system based on DNA as a base. So that is another alternative for the design of mechanical structures. So now we also at our place developing a software, and it is almost finished. We are yet to publish. That's why we are not named here. So in Photon we have written, and along with the Linux bash script we have compiled everything. And we are yet to progress. Okay. So that's all, sir. Now any questions I can ask?
Yeah, thank you, Shivkumar.
Yes,
Any
sir.
questions from audience? From audience, any questions? If there is no questions, we will move to next presentation. Thank you, Shivkumar.
Okay, sir. Thank you.
Yeah, next presentation is by Nilofer. Nilofer is going to present on green synthesis and characterization of copper oxide nanoparticles. Nilofer from Jairam Arts and Science College, Salem. Yeah, Nilofer, you can share your screen. Are you there, Nilofer?
Nilofer is not available, so we can move to the next presenter.
Okay. The presenter is not available. Okay, we will move to next presentation. Next presentation by Josna Bharadwaj. She is from LMN Institute of Information Technology, Jaipur. She is going to present on low energy ion irradiation study of CuC60 nanocomposite, an emphasis on tuning the optical structure of nanocomposite thinking. Josna Bharadwaj, you can share. You can make full.
So my screen is visible?
Yeah, visible. You can make full screen.
Yeah.
Right.
Good morning, everyone. I'm presenting my paper on low energy ion radiation study of copper C60 nanocomposite, and emphasis on tuning the optical structure of nanocomposite thin films. So these are the contents: introduction, application, experimental procedure, characterization, acknowledgement, and references. So what are nanocomposites? Composite materials which are made up of two or more constituent materials with significantly different physical and chemical properties. They are when combined together to produce a material with characteristics different from the individual components, and if the size of at least one of the component constituent is in nanometers, then the composite is nanocomposite. So these are the nanofillers. If we incorporate these nanofillers into this matrix, the nanocomposite is formed. These are the various applications of metal fluorine nanocomposites. They are used in optical nanosensors, optoelectronic devices, optical limiters, biomedical, and they are used in the active layer of organic solar cells. So this is a basic mechanism of ion radiation. Ion irradiation is divided into two parts, that is high energy ions and low energy ions. High energy ions are the ions which have energy approximately equal to 1 MeV per AMU, and low energy ions have energy approximately equal to 1 keV per AMU. Electronic energy loss dominates at high energy, which give electronic excitation and ionization, whereas nuclear energy loss dominates at low energy, which gives collision cascades. Primary radiation effects responsible for modification of materials are collective electronic excitations, which are known as plasmons, breakage of bonds or cross-linking, generation of phonons leading to localized heat of the target, displacement of atoms in the bulk of the target, sputtering of atoms from the surface, generation of ion tracks by high energy ions, and defect annealing and defect creation. So experimental procedure, we have synthesized CuC60 nanocomposite thin films by thermal co-evaporation method. C60 was evaporated by using tungsten boat in a high vacuum chamber. 0.12 angstrom per second was the deposition rate, and we have synthesized our thin films up to a thickness of 30 nanometers. The value of electronic loss and nuclear loss was calculated by shrimp code, which came out to be 66 and 55 electron volt angstrom with a projected range of 972 angstrom. After synthesizing our samples, we have taken it to Kurukshetra University for ion radiation at 120 keV AR ion beam at different fluences ranging from 1E13 to 3E16. This is a basic schematic diagram of what we have done. This is the vacuum chamber, our thermal evaporation unit. We have placed copper powder and fullerene at different tungsten boards, and we have evaporated and synthesized our CuC60 nanocomposite thin films. And after that, we have irradiated it with ion beam at 120 keV AR ion. And we have observed that the size of the particles have increased from 5 nanometer to 11.42 nanometers. These are the characterizations which we have performed. This is a UV spectra of pristine and irradiated CuC60 thin films. We have observed a sharp SPR peak of at 680 nanometers, which was further red shifted to 847 nanometer and again blue shifted to 768 nanometer. This red and blue shifts are responsible due to two phenomena. Number one, when particle size increases, the nanoparticle size of copper nanoparticles increases, then SPR shifts to red shift occurs, and when the refractive index of the material changes, then the blue shift is observed. This is the Raman spectra of pristine and 120 keV AR ion radiated thin films. We can observe the dominant peak of C60 fullerene in the pristine sample, and after that our pristine sample has after ion radiation, it is converted to amorphous carbon. So this is the C60 fullerene is converted into amorphous carbon. That is why the refractive index has been changed and blue shift has been occurred. This is the TEM images. This is a TEM image of pristine CuC60 nanocomposite thin film, and this is the TEM image of CuC60 3E16 irradiated thin film. So we have seen the increase in the nanoparticle size. A nanoparticle size increase from 5 nanometer to 11 nanometer. Conclusion: CuC60 nanocomposite thin film was synthesized and were irradiated 120 keV AR ions. We have seen a SPR peak at 680 nanometer for pristine, which was redshifted to 847 nanometer at 1E50, and then exhibits a blue shift at 768 nanometer at a highest fluence of 316 ion per centimeter square. The characteristic peaks of fullerene C60 was observed in pristine, which was gradually transformed into a broad band, resulting into the transformation of fullerene C60 into amorphous carbon. The size of the nanoparticle was increased from 5 nanometer to 11 nanometer. The small nanoparticles distributed across the thin films, when undergoes low energy and irradiation, forms a bigger nanoparticle due to diffusion and nucleation growth mechanism. The increase in the size of the nanoparticles results in the redshift of the SPR wavelength. At the highest fluence of 316, fullerene C60 completely transforms into amorphous carbon, which gives a blue shift by changing the refractive index of the medium. So this is an acknowledgement. We are thankful to Optical Materials Lab, MNIT Jaipur, IUAC New Delhi, MRC MNIT, the financial support of DST New Delhi, the financial support of UGC, DAE, CSR, and also to the Kurukshetra University. These are the references. Thank you.
Thank you, Joseph Bhargava. Any questions from audience? If there is no questions, we will wind up today's session. We have completed all 7 presentations. Yeah, Pushpendra.
We'd like to thank Dr. Anji Reddy Polu sir for being with us for judging this session. With this, we have come to the end of all the 4 sessions that we have. I request all the participants to actually join for the valedictory session from 2:10 p.m. Also, Reddy sir, if it's possible, if you can send us the marks, we can actually discuss this poster presentation.
Within 5 minutes, I will send it. Just now,
Sure. Thank you. Thank you.
Yeah, sure.
So with that, we will end the session. It was a fruitful session, and I request MIT University, the host, to end the event. Thank you.
Thank you, sir. Thank you.